Thanks everyone for coming to the Temporal Graph Reading Group today. We are very excited to host Rishabh from Stanford again here to present his recent work on relational transformer towards zero-shot foundation models for relational data. Um, so I will do a quick speaker intro. Uh, so so Rishabh Ranjan is a third-year PhD student at Stanford University, co-supervised by Yuri Leskovec and Carlos Gustrin. His primary research interests lie in building foundation models for relational data, which includes databases, tables, graphs, and time series data. Notable works include uh, the relational deep learning, RelBench, and relational transformer. And before Stanford, he was a visiting researcher at CMU, hosted by Zachary Lipton, and completed his undergrad at IIT Delhi, where he was awarded the President's Gold Medal. And you can also find his website on the speaker bio section of the Reading Group website. So I will hand the mic to you. Um, yeah.
Thanks, Andy, for the introduction. Hi, everyone. Very happy to be here. I will be presenting our recent work titled Relational Transformer towards Zero-Shot Foundation Models for Relational Data. It has been accepted to ICLR 2026, and we submitted an early version to the AI for Tabular Data workshop at NeurIPS 2025, where it got an oral presentation. I would like to keep the talk interactive, so please interrupt me if you have any questions or need some clarifications or have some thoughts to share. This work is with a lot of co-authors. Many of them are from Stanford, and many of them are also from SAP. SAP has been very generous to support this research. In fact, I was a summer intern at SAP last summer, so part of this work was done there. So let's get into it. So this talk will be about relational foundation models, and in particular, relational transformer is an architecture towards building relational foundation models. So what are relational foundation models? What is the relational word here? Relational refers to relational databases. A lot of structured data in the world resides in relational databases in domains like e-commerce, finance, healthcare. In all these domains, the information is organized as tables, and then there are connections between tables. So to take one particular example, if we focus on the healthcare schema, there may be tables recording patients, visits, doctors, and individual records, and then maybe rows in the records table refer to patient's table via the patient ID. Here, the patient ID would be the foreign key in the records table, and in the patient table, it would be the primary key. And so this kind of data has tabular, but also graph structure as well as temporal structure, because a lot of these tables will have a time column which records the timestamp at which an event happened, for example, at which the record was created. And when you have all this structured relational data, you also want to do predictions on them. And these predictions are very critical in real world machine learning applications. Example questions are, what will a particular user buy next? Or will a particular user churn soon? Is a transaction a fraudulent transaction? Will a clinic have high appointment demand in the future? Is a patient at high risk for hospital readmission? And the current way to do this is to train custom machine learning models for each question individually, which requires a lot of expertise and a skilled team of data scientists to work on these models. The promise of relational foundation models is to replace these custom ML models with one pre-trained model that can handle all of these kinds of predictive queries on any kind of database, irrespective of the schema, irrespective of the domain from which the database comes from. So, so this is going to be especially impactful for enterprise data because a lot of data in enterprise settings is stored in relational databases. So I thought it would be useful to discuss what the non-relational foundation models for enterprise data are currently, and these can be single table foundation models like TAP-PFN, which has become very popular and impactful. Time series foundation models such as Google BigQuery's Times FM model or Amazon's Chronos series of models, and graph foundation models, where there has been a lot of research interest, but I couldn't really find an industry model. And the relational part of the message here is that maybe we should have a unified research effort towards building relational foundation models because it unifies uh, the preceding kinds of foundation models with a very powerful, very general, and widely used representation of data. And so the relational data model was proposed by Edgar Cord back in 1970. He got a Turing Award for it, and it has sparked like billion-dollar industries around databases. And as I said before, the information in a relational database is organized into tables which have columns and rows. And importantly, columns in one table can refer to columns in another table. So, for example, in a transaction table, the customer ID column is a foreign key which refers to the customer ID column in the customer table, where it's a primary key. And even though relational data subsumes tabular data, time series data, graph data, none of the existing foundation models that I showed in the previous slide work directly for this general case of relational data. However, this is an emerging area, and there have been recent works which have tried to develop foundation models both in academia and industry. So our work is one of these papers. There's a foundation model called Kumo RFM from Kumo, which is a URA's startup. There's another work from a team at Amazon, which is titled Griffin, towards a graph-centric relational database foundation model. And after my internship at SAP, SAP also released a new class of models they called relational pre-trained transformers, um, based on relational transformer kind of architecture. And this model, there's an open source version of this model, but there's also like a small version and a large version, and all of them are available via API access for people to try out. And this. So this shows that there's a lot of interest both in academia and industry, and especially backing from like a company like SAP, which has a lot of relational databases and a lot of customers relying on those relational databases. So that said, now we can get into the more technical parts of this paper. And before going into the architecture itself, I would like to set up the problem, which is around zero-shot relational learning and why the zero-shot piece is important in our setting. So here are some motivations or examples of the kinds of scenarios where you can expect a relational foundation model to be very useful. Um, as I said, the alternative to using a relational foundation model is to develop a custom ML model for each task that is like specifically tied to your database. And this custom model requires a lot of expertise, that is skilled data scientists, but also a lot of resources such as time and compute to train such models, right? But there are a lot of database users who cannot afford this custom model development. Relational databases are very ubiquitous, very prevalent. So, for example, a restaurant has might have a database for its inventory, and it might want to estimate what are the ingredients that will run out of stock in the future. A school has a database of students, courses, teachers, grades and so on, right? And maybe it wants to flag students who are at high risk of failing in the future. Or maybe a website developer wants to add uh, an autocomplete feature to a web form which is backed by a relational database. And even at larger organizations where you can afford to have dedicated data scientists to build custom models, having a relational foundation model would accelerate the iteration stages or the prototyping. For example, you can quickly answer questions like, does removing location data hurt sales forecasting, by querying the relational foundation model once with location data and once without location data. And this frees up the team also to focus on maybe more high stakes models, such as in a banking setting, maybe the model that tries to predict loan defaults, and leaves the less critical ones, such as targeted, like how should we target our sales offers, to zero shot relational learning. So with these motivations in mind, the problem formulation for zero shot relational learning is that the model is expected to predict on a new target, like predict a new target on a new database, potentially with a new schema that has been unseen during pre-training. So there's no database or task-specific training involved because we cannot know beforehand what are the scenarios where the foundation model is going to be used in. And so all the information about the new database and the new task are supplied via the context window, and the model has to rely on in-context learning to make a prediction. And again, the reason we are interested in this particular setup and maybe not the more general setup of fine tuning or training based adaptation is that we want to train one model beforehand that can be applicable to many different settings, and different companies have different data that is proprietary and sensitive, so we cannot expect them to provide that data for our pre-training purposes. And even within that data, each company has its own specific customers, products, etc., which is not part of the pre-training data. Similarly, the prediction targets that you're interested in are specific to the particular domain and application area. And with the problem formulation out of the way, for the rest of the talk, I'll be using this running example for the database and task. And this is an actual database called RelHM, part of the RelBench benchmark. Um, and this data set originally came from a Kaggle contest organized by H&M, the fashion company. And this Kaggle contest was called Personalized Fashion Recommendations. And so we took it and we repackaged it as rel hm. It has three tables. One is an article table, and you can see it has a lot of columns describing the article. There's a customer table, which has a few columns giving features for the customer. And finally, there's a transactions table, which tells you which article was bought by which customer at what time. So there's a TDAT column, that's the timestamp, and also some other features like price and sales channel. So it's a fairly large database with like a few million rows, 33 million rows and 37 columns. And on this database, we have multiple tasks defined on Relbench. For this talk, let's use as running example the item sales task, where we want to predict the total sales of an article in the next week. So here the prediction horizon or like the forecasting horizon is 1 week, right?
Can I ask a quick question? Just
Sure.
a quick clarification question. So when you are
Mhm.
talking about foundation model, do you consider that the goal of foundation model? So I agree with everything you said about the motivation, but do you think a foundation model should also be able to eventually beat models trained on single data set, especially if you consider many of these, the task-specific data sets are very limited in scale and the distribution that it can see. So then with a foundation model, you should be able to generalize this and bring over patterns that are potentially hard to catch from your local data set, but can be learned across a broader, let's say, pre-training data set and so on.
Yes, I 100% agree with you on that. Yes, ultimately, even with in-context learning alone, the foundation model should be able to do better than training task-specific models, especially in limited data regimes like you described, where the foundation model can benefit from patterns it has learned from external sources, whereas a task-specific model does not have access to those patterns. Or maybe the task specific model can be fine tuned from a pre-trained model. So maybe that's not that strong a point. But also, empirically, I think we see promise in that direction. So even in this paper, the our zero shot results are already at 94% of fully supervised task specific training results. So, so already relational foundation models can perform very close to training task specific models. And I'm sure as the research matures, we will maybe even outperform them. And we have seen similar things happening in the tabular foundation model world, where current tabular foundation models can outperform XGBoost, LightGBM, and other baselines which have been trained specifically on that task.
Yeah, makes sense. Yeah. Thanks for the
Thanks for
discussion.
the great question. And please feel free to interrupt and ask any clarification questions or general questions. Yeah. So now that we have this running example, I want to talk about what is the context window for the relational foundation model. Because this is not text, it is harder to visualize the context because it's not simply a sequence of words. Here, the context is a selection of rows from across different tables. And so on this slide, I have a tabular visualization of a real example from this for this real database and task. And I will walk through the how this table was constructed in the next few slides. So you start with a row, or maybe let me also point out that in the schema, we had three tables, article customer transactions. Here we have a fourth table called item sales, which is a task table, which we introduce just to formulate the task, as in the sales column has to predict the sales, the label that we are interested in, and the timestamp column tells you at what time the prediction is being made. The article ID tells you for which article you're making that prediction. And so we start with one row from the item sales column, which captures what we are interested to predict. And the cell value that we want to predict is masked. And now that we know that this is the article ID, we extract that article row from the article table. And then we find the transactions that this article is involved in. Based on those transactions, we find the customers that are involved in those transactions. And then based on the customers, again, we find some article, in this case, 2251, which we retrieve again from the article table. So you might have realized that this is kind of a breadth first search algorithm going on. And that is clearer in the graph visualization for the context, where you start with a node. So here the rows in the database are nodes, and then you follow the connections based on foreign and primary key links. That's foreign to primary key link, and construct maybe a few hops of a local subgraph there. And at this point, you might be wondering, we're talking of relational foundation models, but we already have a general foundation model, which is large language models. And if I have this context, can I not just serialize this in some format and ask a large language model to do a zero-shot prediction? And you can technically do that. We have tried it. In fact, we have a baseline in our paper showing the results, but it does not really work very well. And the reason is that database prediction is not sequence modeling. These models have been trained for a particular structure, which is a sequence of tokens, and they've been trained on text data, but databases have a very rich relational structure with columns, rows, links, and so on that is not effectively modeled. And further, the text serialization is very bloated. It's very expensive and requires very large context lengths because again, you're trying to express something which is not a sequence as a sequence. And so here I'm showing an example of a JSON-based serialization that was proposed in the paper tackling prediction tasks in relational databases with LLMs. And this simple context that we have from the last slide, like just this many rows, 39 plus 21 plus 14 plus 7, that gives us a context length of around 10,000 tokens. And for some other databases, it's even worse. And moreover, if you see the text that is produced, it's just a wall of text, and it's like going to be very hard for an LLM to make any predictions based on that, because to make a prediction, you have to identify patterns in the database. You have to capture predictive signals which might be spread out across columns or rows or time or links. And for example, in this case, even to look across or to attend across a single column, you have to first figure out that, there's a product code is maybe a column name, and then the product code appears many different times in this whole prompt. And then you match the product code 561445 with product code 561445 in some other sentence. And based on that, you do like a one hop message passing, which is going to be very hard for the model. And hence, in this work, our approach is to design a transformer architecture from the ground up for relational data, keeping zero-shot prediction abilities in mind. And so we had a few design principles. One is you want to effectively capture the relational structure. The second is this is a foundation model. We want to pre-train it. And so we should be able to pre-train it with some simple self-supervised objectives. And finally, because this model has to work on any new database, on a new task, the architecture has to be schema agnostic, as in it can work with any schema. And this is not true, by the way, for a lot of graph models that are out there because they are tied to the specific node types and edge types that the model has been trained on. Because the weights in the model themselves are specific to a particular node type. And so we have a bunch of innovations for meeting all these design criteria. To effectively capture relational structure, we introduce novel relational attention layers. To support self-supervised pre-training, we adopt a cell-level tokenization. So every cell becomes a token for our transformer, and then we have a simple masked token prediction objective to predict the masked cells. And finally, to enable schema-agnostic zero-shot generalization, we adopt a few things. One is we use task table prompting, which can frame any task as masked token prediction. So this is similar to introducing the task table in my previous slide and then masking a cell in the task table. We rely on cell data types, which can be numeric, text, Boolean, or datetime. And these are universal. These are shared across databases. So having encoders for these primitive date types transfers and generalizes well. And finally, relational attention is constructed based on universal primitives like rows, columns, foreign keys, and primary keys. Um, With that out of the way, here is the overview of the relational transformer architecture. In the next few slides, I will go over different components that are in this picture. So we start with a schema. In this case, the schema follows our running example of RelHM item sales, where you have maybe a user table with user ID and gender, sales table with time, user ID, item ID stars, an item ID table with item table with item ID, price and details. And again, you have foreign keys and primary keys. On this, maybe you want to predict the total sales over the next week. That is the task or the predictive query. And this is where task table prompting comes in. In order to predict this task, uh, we introduce a new table called the task table, and it has these three columns: the time column, item ID, which refers to which item you want to make the prediction for, and a label for what the actual prediction should be. So this way, the model knows what task it's performing based on like maybe other rows in the task table, and making a prediction is as simple as filling a masked cell in the label column. And so from the architecture side, this table is not treated any differently than existing tables, which allows for a seamless transfer between masked token pre-training to inference. Once we have the schema, we want to make a prediction for a particular target row in the schema and in the database. And for that target row, we extract a graph, a subgraph, and express it as a collection of linked rows. So in this case, for example, this last row here is the target row. It has some time value and the label value is masked. And it also has links to the item, to some rows in the, to a row in the item table and so on. So there's like a whole graph structure. We also have table names and column names to provide some semantic information to enable better zero-shot generalization. And the other rows from the task table serve as in-context labels, which help the model learn how to make a prediction for a completely unseen task and a completely unseen database. Once we have the context window every cell in the context window becomes a token for a new transformer, for our transformer. We do not use positional encodings because unlike LLMs, again, we are not dealing with a sequence of tokens. So as our input to the transformer, we just have a set of cell values, no positional information. We do not even use graph positional encodings. The relational structure will be captured by the attention layers later. Once you have the set of cell values, you want to convert them to a shared embedding space to get token embeddings. And for this, we use a per data type encoder, which is specific to numeric, text, Boolean, or time and time data types. And then we also add the language model embedding for column name and table names to inject semantic information. Once you have the token embeddings, we pass them through a series of relational transformer blocks. The relational transformer blocks are similar to standard transformer blocks, except for relational attention layers. We have three kinds of relational attention layers: column attention, feature attention, and neighbor attention. And I'll show visualizations for what these three attention layers are doing. And after the transformer blocks, we have a per data type decoder, and specifically we use the decoded token corresponding to the masked token as the prediction, right? So now we can understand what the relational attention layers are. For comparison, here's the full attention layer, which is a bidirectional attention. And for any query token, it is allowed to attend to any other token in the context. Column attention restricts the attention to only tokens in the same column. So this allows the model to understand which column it is in, what is the distribution of that column, what are other values in that column, and so on. Feature attention restricts the attention to the features of that cell. So other cells in the same row, but also cells that are in parent rows. So for example, if a transaction row has a user ID column, we also allow that cells in that row to attend to the cells in the actual user row. And finally, there's a neighbor attention, which allows attending to neighbors in the graph sense across like primary to foreign key links. And this is the entire architecture in brief. These attention layers are very easy to implement with Flex Attention, which is a new, or maybe now at this point it's 1 year old, but it's in PyTorch, and it allows you to get the same performance as handwritten flash attention based kernels while being able to express your attention variant simply in Python. So this was very useful for us. And I just have this slide to show the kind of attention masks we construct to implement the different attention layers. And maybe the most interesting is the column attention layer, because once you serialize the tokens in a column major order, then you get a nice block sparse structure or block diagonal structure for column attention. And so what this means is that the GPU only really has to compute for everything that is yellow, and everything that is purple is masked out and is not even computed on the GPU. So the point maybe here is that column attention is kind of linear, in scales linearly almost with the context length, and not so much quadratically with the context length. And the same holds for the other attention variants too, although it's not visible in this slide because we are showing a very small context length. So with the architecture and implementation out of the way, here's the pre-training setup that we used. So we used Relbench databases. Relbench has 7 diverse datasets across e-commerce, social, sports, and medical domains. There's a large variety of uh, tables, rows, columns, and even time spans. But 7 is still limited. So we adopted a leave one database out evaluation. So we would train on 6 databases and evaluate on the seventh database. So importantly, the database on which we are evaluating has never been seen during pre-training. We use mass token prediction. We train on both classification and regression together. So the same model does both. For classification, we use binary cross entropy. For regression, we use Huber laws. We just add them. And each training run, as I said, uses only 6 databases, but for each database, we define around 20 tasks, which can be forecasting tasks where you're trying to predict a future derived quantity like item sales, or it can also be a simple autocomplete task where you're just predicting an existing column in the database, but there's still a temporal constraint that you have to predict it based on only the past values. Because we had to do a lot of pre-training runs uh, and ablations, we restricted our model size to a very small 22 million parameters. We trained for 13 billion tokens, and this is very accessible at academic compute. It takes 2 hours on 800 GPUs to complete one pre-training run at 1024 context length. And now we can go to the results. But I mean, if there are any questions about the architecture or pre-training at this point, it would be a nice place to stop and discuss.
Yeah, I'm a bit curious, and maybe that depends on how you're training it. So, 8 A100s for a 22 million parameter model, that seems like a lot of GPU for a small model, right? Or
I mean, we're also training it for 13 billion tokens. So that's a lot of steps.
yeah, I was just wondering if you use the extra GPUs to speed it up, like if it couldn't fit on a single GPU or
Oh, it fits on a single GPU. Like the memory is not a concern. It takes maybe what, less than 10 GB of GPU memory.
exactly. Yeah.
Yeah, but we just use it to speed it up. So we have a DDP setup.
All right. Cool. Thanks.
Yeah. Yeah, thanks for the clarification.
I have another question about the leave one out experiment. You keep
Mhm.
one database unseen by the model. Like, what about the entity types exist in the unseen database? Is it completely unseen from the other databases used, or some of the entity types already exist in the set of the training database?
Mostly it's completely unseen because here are actually all the 7 databases, 1, 2, 3, 4, 5, 6, 7, and they're very diverse. They're coming from very diverse domains. There is maybe some similarity between Amazon and HM, but very at just a very high level. Like Amazon has customers, HM has users, and so you can say, okay, both are e-commerce data sets, both have users and products and so on. But other than that, there is, yeah, the entity types are not seen.
Yeah, makes sense. Thank you.
Um, and also a quick clarification question, and maybe I missed a detail, but how many hop are you looking at for the neighbors?
So in one neighbor attention layer, we just look at one hop.
Okay. And how many,
And
yeah.
sorry.
And how many, like how many layers you have? So that would be how many hops, right?
Yeah, so we have a total of 12 layers. So I don't think this corresponds to 12 hops because the context does not have that many hops. But in context sampling, we we keep doing breadth first search till our context runs out. And for these databases, it gives us maybe like 4 or 5 hops max.
I see. I think the only data set that might have like 10 hop or something is like rel trial, I think. So maybe that one you don't fully saturate the hops potentially.
Yeah,
But yeah.
that is a very good point, and I can also share you with you some experiments we have internally
Hmm.
where for rel trial, if you keep the BFS width very small
Hmm.
and keep increasing the depth, the model's performance keeps increasing, which is basically what you're saying,
Right. Makes sense. Makes sense.
right? And
And
it's like
yeah,
it increases by a lot, which we were very surprised. We thought it was a bug, but then we figured, yeah, it's just
makes
the
sense.
nature
It
of the
needs more
data.
hop. Yeah.
Yeah.
Um, okay, so then one last question about this. So you said the leave 1 dB out. So I guess so I guess so when you leave out the trial, I would expect it to be the hardest for the model to generalize to if you train on the other ones because this is the longest hop. So the model never really learned to leverage, let's say, 5 hop information or something, right?
Yeah, you are right. We see worst results on rel trial, basically almost close to trivial baselines.
Right.
Sorry, but it's also for it's for two reasons. One is for this paper's experiments, we use the same sampling parameters for all data sets. So for this paper's experiments, even rel trial is only on a few hops.
Right.
So you
Right.
already don't have enough information in those few hops, and then you're only trained on a few hops. So
Mhm.
for both
So
reasons.
then, so then do you think the problem is more with lack of data set and scaling law rather than architectural changes? Because it seems like if you just have sufficient data, long range data, then you can be
Mhm.
able to cover everything, right?
Yes, yes. And that's what we are finding in like our current projects also, where we are trying to scale up.
Hmm.
Like
Hmm.
architecture, we haven't changed a lot and we're still getting good results by just scaling the context length and the scaling the data.
Hmm. Hmm. Makes sense. Thanks.
Okay.
I have a quick question related to the hub question. So
Mhm.
is the implication that if you're dealing with a data set where each record has a high number of degrees, then your context is going to be limited. Your number of hops is going to be limited by the context size. So if you have a database where the number of degree is low, then you can have a potentially very deep search.
That is true. We also have a width bound on the BFS. So, for example, in this paper, we use a width bound of 128. So even if you have a degree higher than 128, we'll just sample 128 edges randomly and use those. Because more than 128 edges does not really give you any more information about the task. And it's like better for the model to look at deeper information at that point.
Okay,
It's like
interesting.
a heuristic, yeah.
Yeah, and so the diverse data sets, I guess my question is, does that mean when you try to apply this pre-trained model to a completely different domain, let's say, that
Mhm.
your obviously performance is going to be much worse than the existing domains?
Surprisingly, that's not always the case. For example, rel F1 is a sports domain that's very different from everything else, but we get one of the best zero shot results on rel F1. So the model really learns to do in context learning to figure out how to make the prediction. It's like not tied to a particular domain.
Have you found that to be true in other domains?
Um, so yeah, rel event, rel stack, also we get really strong results. I guess these are e-commerce is the most represented domains, so here you expect to get strong results. But okay, in the results section, maybe we can focus on event stack and F1, and I'll show you the results. Uh, okay, if there are no more questions,
I
then
have
I can.
another quick question.
Okay, yeah.
About the schema correctness. Does it has any impact on the final quality? Because I can design the same database using two different schemas.
Uh-huh.
So did you try any like experiments on that?
Oh, we did try this for some recent stuff we have been doing with Railbench version 2, where we are trying to incorporate the temporal graph benchmark as relational databases. And you have a design choice how you want the schema to be. And we tried a few different schema variants to represent the same underlying data. And the results were comparable. So yeah, the short answer is maybe it does not impact that much, but we have very limited experiments, so maybe in different settings the impact will be higher.
Yeah,
Yeah,
thank you.
and just for my personal interest, did you include it at the end or?
Yeah, we included, so I have a slide on that,
Okay,
but it's on Relbench V2. I mean, the PR is still open, but very soon it will be on Relbench V2. We also submitted a paper, so the
nice,
paper is on our archive and it describes our results and experiments. Yeah.
nice, nice. Thanks.
um
I have a question too.
sure.
So really great work. I've been following this for a couple of months. And my first question is, how does this scale to like really potential enterprise data? For example, like the place that I worked earlier, we had close to 70 to 100 tables with very complex relationship between tables. It's not just the direct primary key foreign key relationship. The schema itself was very complex. So just curious to know with such a case, how does this handle? They were also like, let's assume 100 million rows of data.
Yeah, thanks. We haven't had a chance to work with that kind of scale, although I was hoping to work with some of SAP databases which have similar characteristics, but this is very early stage, I guess. But the good news is that the model architecture is decoupled from the context. So really, this is more of a context sampling problem where you have to decide what information is most relevant to make the prediction and put that information in the context. And so, for example, you can put disconnected subgraphs in the context, and there is no like the architecture still works. Whereas in a GNN, for example, there will be no information exchange between disconnected subgraphs. That is not the case here. So the architecture itself is not limited to foreign primary key links or to the particular way that we are sampling or like too small number of tables.
But yeah, one more question. Like,
Mm.
just like how we have uh, like relational DB optimizations where we do like query optimization, like improvise the join clauses and whatever. So what do you think if we have such optimizations implemented at the attention level, for example, let's say we have a join between two tables, information about joins of the tables or other potential ways that we similarly do in DBMS can be implemented here, which can boost the performance, like speed up the.
Yeah, so again, that's a very nice question. I would again say that this is less of an architecture concern, which is a good thing because like the architecture is decoupled from the context. But on the context side, I'm sure doing or like trying a lot of variants will show that some variants maybe do better. And so the an analogy I will draw here is to prompt engineering for large language models, where for the same task, you can express prompts in different ways or put different information in the prompt. And the same pre-trained model can give you better results by optimizing the prompt. In the same way, even for relational foundation models, we expect uh, some kind of context engineering or prompt engineering to boost results. So maybe joining two tables would help because it brings information closer together and so on.
Got it. Yeah. Thank you so much.
Thank you.
I had a quick follow-up, sorry, just a quick follow-up to the context engineering point. Do you think it's possible in the future where I wouldn't have to do like specific context engineering and I can like learn what kind of rows in this case would be very important to sample for my context window? Like, basically instead of specifically knowing
Yeah.
this, for which I would need the domain knowledge, can I do this in a domain agnostic way where the model itself learns what is important for the context?
It will have to be a different model because the
Mhm.
context sampling problem is you have billions of rows in the database and you have to decide which rows to include.
Yeah,
And so you need a way that can work on billions of rows versus foundation models will have a limited number of tokens and can never work across billions of rows. Maybe you can have some kind of an agentic solution where an agent decides
Mhm.
based on the domain and task what rows will be important and fetches those. But that's on the retrieval side. So
Yeah.
here we are talking, something like a RAG system where you have a
Mhm.
retriever that decides what information is important, and then the relational foundation model is more on the augmented generation side.
Got it. Got it. Yeah, I think, I was also thinking something along the like lines of RAG. I think that would be pretty interesting
Mhm.
as the problem itself. Also, just another unrelated question. I think this was like a follow-up from Andy's question where he asked about, task-specific models versus foundation models and whether we think foundation models will outperform task-specific models. But
Mhm.
do you feel like there might be a point where we need to have so many more parameters for foundation models to approach like even the idea of outperforming these models, and then at that point it just becomes less efficient to like it just becomes a better user source to just train your own task specific model. uh, so maybe we don't really want to get to that stage even. uh,
Yeah, I
yeah, I don't
mean,
know.
these things depend really on the problem characteristics, and I'm sure there will be settings where RFMs shine, where you maybe need the zero shot abilities or a few shot abilities more than the inference latency. And on the opposite extreme, maybe you want very small task specific models. But
Mhm.
hopefully, more of this spectrum will be covered by RFMs as we make more advances towards like efficient, scalable models.
Gotcha. Yeah, thank you so much. Really enjoyed the
Yeah.
talk. Thank
Yeah,
you.
thanks for the question. I we just have a few minutes, and all my results section is left. But let me quickly go over the most important results then. So for zero-shot binary classification, we compared with GEMMA models at different sizes, and they see the same information in the context as we do. RT is ours, where we do not pre-train on the particular database, and then we do some continued pre-training on the target database to get even better results. And if you just focus on the mean AURC row, the entity mean baseline is a very simple non-neural baseline that just predicts the like mean of the labels for that entity, and it's better than all the JAMA models on average versus RT is 70.1 without target data set in pre-training and 72.9 with continued pre-training on the target data set. So we are a lot better. And then if we look at rel F1 results, it's 89 AUC or else stack results, which is like 77 or 80 AUC. So this answers the previous question where even if the domain is completely unseen, the zero shot performance can be very high. Um, and the point here to note is that the Gemma model, which is an LLM, has or RT compared to Gemma has 1,000 times fewer parameters and 10 to 100 times lower context requirements because of how we tokenize every cell as a token. And this leads to 100,000x fewer inference flops. But despite that, we are getting much better AUROC than that. And this says why we should focus on developing relational foundation models rather than trying to shoehorn LLMs to solve these kind of problems. And that's for classification, which is very simple. You just have to predict true or false, or yes or no. But for regression, where you have to predict numeric targets, LLMs are basically unusable because most of the LLM results are highly negative. So R square being negative means it's worse than just predicting the mean of all the labels in your data set. So the LLM cannot even do as good as predicting the mean of all labels. Whereas the entity mean baseline gets 19.3 R square and RT gets 26.4 zero shot R square. So it's like a lot better than a simple baseline. And again, for F1, which is a completely different setup, it has a very high R square of 58.4. And we also have results on self-supervised fine-tuning, where we see that pre-trained RT is the best in all settings, in low, medium, or high resource settings. And you can see that from this solid blue curve, which is like dominates every other curve across different fine-tuning steps, right? I will skip this slide for interests of time. Here we show some test time compute scaling. So at test time, if you increase the or decrease the context length of the prompt, you can increase or decrease the inference time or inference memory. And based on that, the performance also increases. But we see that at any resource constraint, we give RT gives much better results than the most comparable baseline, which is a 22 million parameter GNN based foundation model called Griffin. Um, we have some ablation studies that I will skip again in interests of time, but we ablated the importance of using semantics such as the column names and table names, and we found that it does matter. The performance does drop by removing in context labels and schema semantics. And then among the different attention layers, column and feature attention are the most important for zero shot performance. As you can see, performance drops from 22.8 to 11.9 if I remove the column attention. If I remove feature attention, it drops to 18.8. And the intuition there is that column attention helps to adapt to new column distributions, and feature attention helps to adapt to new entity types. And this is especially important if you're testing on data sets that you have really not seen in pre-training. And so I'm almost at the end of my talk. I just wanted to give a sense of what we are doing with this direction going forward. So one is we really want to train on a lot of data. And so we are doing large scale data curation. We have RelBench V2, which is now on archive. You can also just visit the RelBench link. And we released this a few days ago, where we have 4 new original databases, lots of new tasks. We have external integrations. So we have 70 plus databases from CTU now, data sets from other benchmarks. Recently, we also added TGB, which is the next slide. So TGB is now in RelBench V2. We have an entire section discussing TGB in the paper. And this is what the statistics look like for TGB converted to relational data, where we have mostly a small number of tables, like 2 or 3. But for heterogeneous graphs, we can have larger number of tables, so 5 in these cases. And like for the GitHub ones, we have 18 tables in this particular schema. We also tried another schema which had like 10 tables, which is what I was saying before, and it gave similar results. So this is pretty exciting. And then finally, real data is not going to be enough, or like even if real data is going to be enough, it would be nice to augment it with synthetic data because people have found that to work very well for tabular foundation models. And we recently archived this paper called Plurel, Synthetic Data Unlocks Scaling Laws for Relational Foundation Models. Uh, the first author, Vignesh, made a very nice website. So it's on snapstanford.github.io/Plurel. Please check it out. It gives a very nice overview of the paper, the main results and takeaways, as well as the method details. And Vignesh will also be presenting this paper at the TGL reading group next week. Please join us uh, next week, February 26th, to learn more about how we can generate synthetic databases and use that to pre-train models and use that to scale up relational foundation models. And in fact, the scaling up is like so predictable that we were able to fit scaling laws on that. So overall, things are in a very exciting place for relational foundation models. Um, Relational transformer seems to be working well even at this scale. So even for this paper, we use the relational transformer architecture, and and it works very well. Um, and finally, I want to thank all my co-authors as well as other people in my lab who have been very helpful, very supportive in getting this project uh, to completion and like making it how it is right now. So thanks everyone for listening. I know we are out of time, but I can stick around if people have questions or thoughts, any further discussion.
Yeah, thanks for the great presentation, and you can clearly see the amount of interest from the group as from the number of questions. Um, so yeah, so feel free to ask any question now, and also you can also relay the. So I think your contact information is also on the website if you want to send any question by email. Yeah, thanks for the great work, and looking forward to the next one next week on the scaling law side. Um, Maybe just one 30-second question. So you mentioned for the next paper, so for next week's talk, you are using the relational transformer, which I think is so that's like this week's talk architecture,
Yes,
right? Okay.
yes.
Oh, okay. Sorry. Because the naming, I was thinking about the relational graph transformer, which was VJ's paper, and it's just very similar, right?
Yeah,
Uh,
that's a little unfortunate, but
yeah.
hopefully relational transformer is a smaller, cuter name to remember.
Right. Yeah, makes sense. Okay, thanks.
Yeah.
Yeah.
I some questions. Thanks for a really interesting presentation. First of all, so I think one of your and now I'm just kind of zooming out and going back to the motivation behind all of this because I think the work kind of talks for itself and it's really good. But like motivation wise, one of your arguments was that if we're in a setting where we don't have a lot of data, right? So like, transfer learning or like some new database or something, I was wondering about like all of your attention to the different cells and the different rows of the tables. Like, how does that scale? Because in that sense, you would be in a very like low context scenario. So, do you have any ablation studies on like if you drop rows or if you drop like if you work on very, very small databases?
That's interesting. So I've just been thinking about like having larger context lengths.
Yeah.
It's the first time I've been asked about smaller context lengths.
Because to elaborate a bit on my question, like say
Uh,
I'm a very small business owner, I
mhm.
open a new shop, maybe I'm also doing fashion, then I have one row in my data set which is I'm trying to sell this shirt.
I want to know how many people are going to buy this shirt. And of course, I can ask ChatGPT
Mhm,
because
mhm,
it's been
mhm.
trained on everything else, right? But in this sense, I would only have a few features about, and I wouldn't really have any context to kind of put it on, right?
No, that makes sense. I feel like for those cases, like the difference between RFMs and LLMs vanish a little bit. And like you said, you might be better off just asking ChatGPT if there's not too much relational structure to leverage there. Because there you have to make a prediction more based on world knowledge than based on the
Yeah.
context information. Yeah.
Yeah. So do you know like when is that cutoff? When should I, you know, because at some point I have enough data to train like a task specific model, and at some point I don't have enough data, so I'll need to ask like an LLM or something. So like when do you know or do you think that this kind of changes?
So even if you have a lot of task specific data, you're better off fine-tuning a pre-trained model. And
Okay.
this end is like millions of data points. So
Mhm.
if you have anything less than a few million data points, you're still going to get a lot of benefit from fine-tuning a pre-trained model.
Yeah.
Um, but also like the zero shot performance is not that far from like the ultimate fine-tuned performance.
Mhm.
And we are working on this more. So if you increase the context length of the model, you can basically put a lot of your data points within the model's context and
Yeah.
get better results zero shot. So it basically simplifies the model development pipeline where instead of figuring out learning rates and taking care of overfitting and all that, you
Mm.
just query a relational foundation model with some data points and get back the answer to your question.
Super cool. And I think this actually answers my second question which was more like, you know, with tools like Claude Code and all of this, you know, you can basically shake your arm and all of these task specific models drop out because they basically code themselves at this point, right? So I think like in large data domains where you have a lot of data, then you would argue that something like this makes sense.
I mean, I don't know about Claude Code. Sure, it'll be able to write code very easily and will not
Mm.
have bugs and so on. But I feel like the hard part of training a model is not implementing it. The hard part is having the expertise to debug that training. Like, am I overfitting? Should I increase the regularizer? Should I have data augmentation? Is like my model capacity too small?
Yeah.
Like I don't think current agents are at a point yet where, for example, they can do well on Kaggle. It's still
No.
humans winning Kaggle contests, right? And
Yeah.
and and maybe that's the point that if you're asking Claude Code to maybe implement a GNN based solution and have it work well by iterating on hyperparameters and other things, maybe it's going to be more brittle. But if you ask Claude Code to just use RFMs, like to
Yeah.
download a pre-trained RFM and to maybe construct the context in a nice way, put all the relevant information in a context, and do a tool call to RFMs,
Yeah.
that will be much less brittle and much cleaner.
I think at least it would be interesting to benchmark against, right? Because out in industry, I guess that is what many people are doing, right? That they're just like telling Claude Code, go implement an XGBoost and do some hyperparameters grid search or whatever, right?
Yeah, I think we can benchmark against AutoGluon or some kind of AutoML library
Yeah.
where it's not an agent doing it, but like the AutoML library does a lot of model selection, hyperparameter tuning, and so on. So
But
it'll be
but
interesting.
that's but that's primarily in the tabular foundation model domain, right? Whereas in relational deep learning, you still need to do the feature engineering if you need to use AutoGluon.
Fair, fair. I was thinking like Claude also does the feature engineering as part
Yeah,
of
yeah, yeah. Cool.
model development. Yeah, but thanks. These are interesting baselines to compare against.
I yield my time. Thank you for the answers. Really interesting.
Thank you. Yeah.
Yeah, thanks everyone. And then if there's no other questions, we can also wrap up here, and let's thank Rishabh here for the very nice talk and the very engaging discussion today. Yeah, and looking forward to more discussions next week for sure. Yeah.
Yeah. Yeah, thanks everyone for the very nice discussion, thoughtful comments and questions. And please check out our paper for more details. Yeah.
Yeah.
And feel free to reach out to me if you have any other thoughts or clarifications.
Mhm.
Thanks, Andy and Victor, and I don't know if Julia is here, but thanks for organizing this. It's great. Yeah.
Yeah, and thanks again for presenting. Yeah, so see
And
you guys next.
reaching out as well, right? I think that's also nice,
Yeah.
Anyway.
Yeah.
Okay. Yeah. Thanks. Bye.
Thanks. Bye-bye.